Assalamu alaikum. How are you?
Assalamu alaikum, sir.
Walaikum assalam, sir.
Walaikum assalam. Okay. So let me share my screen. So we have covered link state routing in the last class, right? So
Yes, sir.
if you have any question, anybody has any question before we move to the next algorithm, that is distance vector. Okay, let us check what is the basic property, basic feature of link state routing in short, in 2 to 3 words. Anybody? What is the basic characteristics of link state routing? Remember, we have introduced two categories of routing. One is link state, one is distance vector. And there was one fundamental approach in terms of the data, in terms of the topology. So what is the basic feature of link state routing? Can anybody tell me? No, Ashik? Ashik, are you there? Can you tell me? Aziz? Anika?
Sorry, sir.
No idea?
স্যার
Nul-
আমরা
Nuzhat?
তো কারেন্ট নোট থেকে স্যার আমরা তো কারেন্ট নোট থেকে সবসময় মানে মিনিমাম ডিসটেন্সটা নিয়ে কাজ করি না লিঙ্ক থেকে
Right,
Sir,
right.
determine best path.
Right, Shafiq, Nuzhat, I think you are right. Best path, but best path or least cost path, actually, this is the common goal of any routing algorithm. So this is not the specific feature of link state, right? We need more specific feature, more specific characteristics, because every routing protocol will have the common goal, right? Finding the least cost path or shortest path to the destination. Then what is the basic difference between link state and distance vector? Okay, in terms of topology, in terms of the entire database, what is the property of link state? Every node will have complete topology, right? So that is the most basic property of link state. Every node will have. Now, how every node will have complete topology? That is a question, and I think I have also mentioned there is a initial advertisement phase. Each node will send advertisements. Those are called LSA, link state advertisements. So every node will send advertisements through the neighbors, through the physically connected routers. And after a certain amount of time, every node have the complete graph, the vertices and the corresponding edges. So that is what we call in link state. Every node have complete topology before we start the algorithm, right? Agreed or not?
Yes,
Is
sir.
it clear? Yeah. Okay. So when we start, we assume that every node has complete topology. So when calculation starts, there is no more dependency on others, right? Like in the last class, we have solved we have found a routing table or forwarding table for what? For the node U. So we assumed U as the source. It has been said that U is the source. So when I say U is the source, all the calculations are done for U. If you change the source to X, to V, the entire calculation will be different. So every node will start calculation after it gets the entire topology. Clear? Now in distance vector, what we said? There are actually partial topology. So every node only knows up to the neighbors, not beyond that. Okay, what that means? Let us start. This is distance vector algorithm, and the equation we use here is Bellman-Ford equation. Okay, and this uses actually dynamic programming. So Bellman-Ford equation says, okay, how can I? Okay, So the equation is, you can see dxy, and again the goal is same, to find the cost of least cost path from x to y. So x to y, and we have to find least cost path. So the goal is same, but the approach is different. Now in this equation, x is actually source, so x is the source, okay, and y is the destination. So x is source, y is destination. Now what the formula says, minimum of v. Now what is v? Again, this is same, possible next node, right? You remember in the forwarding table we always say what is the next node. So u forwards to x, x is the next node. So what are the possible next nodes? These are represented by, this is represented by v, okay. For each next node, for each intermediate node, in the formula you can see there is a direct cost. So c is, okay, this is already written here I think, so I don't need to write. The direct cost of link x to v, remember I have mentioned c means direct cost. So this is known to the node, that is why we call it partial topology. And the second part is v's estimated least cost path. That means v is the neighbor of x. So in this case you can look like this. Suppose this is the node x, and for example there are 3 possible ways to go y. Maybe p, one is q, and one is r. Okay, this is r. So from each of the cases, we don't know the dotted lines, this is the final destination y. So to x, only visible part is like this part is visible. So that's why we call this partial topology. The dotted part is not visible to x. That means a node only knows the information up to the neighbors. Beyond the neighbors, no information is available. So the question is, if x wants to go to y, how many possible ways are there? How many ways x can move to y? Can you tell me, seeing the picture?
The 3 ways.
Very good. 3 ways, simple. X cannot go other than PQR because x has no other connection. So doesn't matter who is the destination, x must go either through P or through Q or through R. So the idea is simple. Only through neighbors, only through physically connected routers, right? So that's why in this case, what are the possible next node in this example? It can be P, it can be Q, it can be R, right? So now if you use the equation, what you will do? You will keep x and y as it is. So see, destination is here, source is here. So what we are changing? We are changing this one. This is the neighbor node, okay? Is it clear? So if there are 3 neighbor nodes, how many values you will get here? How many possible values? Tell me. Or you can also use your message box. Again, I want everybody to participate. Use your paper and pencil and then do it with me. So according to the diagram, how many values we will get in this equation? Can you tell me? Anybody? Nuzhat?
স্যার মানে কোশ্চেনটা বুঝি নাই ভ্যালুস মানে আমরা
Values means, okay, let me make it clear. In the link state, when you applied the formula, how many values did you get in each application of the equation? in the link state, not the distance vector, in the previous one. How many values did we get every time? Two values, right?
Previous.
One was the previous lowest cost, right? And another was when we go through the current node. Agreed, everybody?
Yes, sir.
Is there any case where you got more than two values in link state? Any case there?
No, sir.
No. Every time we applied the Discustra's algorithm, applied the formula, we got two values. One is the previous lowest, and the one is the current value through the current node. If current node value is lower, then we update it, if you can remember. So not more than two values, not less than two values. But here, it depends on number of options. Number of options means what? Number of neighbors. So my question was, when you apply the equation, if I use the example given drawn on the right side, what will be the number of possible values in the equation? Like what will be three? I think there will be three possible values for V, right? X and Y is fixed. So the intermediate node will change. So how many values we will get?
3 values.
Three values, very simple, because V will be changed. So how many values of V are there? 3, P, Q, R. So there we will get three possible values, and out of three possible values, we will select the lowest one. That is minimum. And for each value, we have two parts. One is direct cost, that is known, right? And one is capital D of V to Y. Now the question is, how X will know the second part? That is the question. Keep in mind that I will just shortly I will explain from where that value comes. But this is the equation we call Bellman-Ford equation we use in distance vector algorithms. Okay. Okay. Now let us take the previous graph, the previous diagram, and understand the Bellman-Ford again. Okay, in this case, suppose we want source U to destination Z. Again, U has neighboring nodes X, V, and W, right? So how many ways we can move from U to Z? Okay, I want the answer. Sorry, Shafiq, how many?
So infinity, no direct as.
No. In this case, in Bellman-Ford equation, in distance vector, if you have the basic idea, it will be clear again. The number of neighbors, the number of physically connected nodes will determine how many ways you can go. It's not like, how can you go from U to any other node other than V, X, and W? Is there any other way? Is there any other way? You can call about how many paths. If I say how many paths, that is a different question. But how many ways we can move? Only three ways. Like who will be the possible next node? Either it will be V or X or W. Is there any other possibility?
No, sir.
No. So that is confirmed. If there are 10 neighbors of you, then how many possible ways? Tell me.
10, sir.
10. So it only depends on neighbor of neighbor. Suppose you, again, if I go to the real life example of that routing, if I go from, for example, Dhanmondi to maybe Asad Gate, then I have several options. You can go through Science Lab, you can go through road number 27, you can go through Mohammadpur bus stand, right? But there are finite number of nodes. If you think about the exchanges are routers. So every router has options. How many options? Number of routers it is connected to. Number of options means actually number of links. So from U, if we want to go to Z, we must go through V, X, and W. So there are three possible options. Now you can. Okay. Now my question is, if we want to, okay, before that, again, we know there are three options, right? So this option is already known. Do you agree? These three options, these three, not options, these three information is known to you because these are with neighboring nodes, directly connected nodes. So 2, 1, and 5, V, X, and W known. All other part is not known. So these three parts, actually I can call this known, okay? This is known. And that's why we call it partial topology, known to you. And the rest of the part, this rest of the part is not known. Okay? Not known to X. Do you agree? Sorry, not known to you, not X. So the basic thing is clear, everybody? So this is distance vector where a node has only information up to the neighbors, and beyond the neighbors, nothing known to you. Now, if we want to calculate, actually we want to calculate what? We want to calculate d u to z, right? We want to get d u to z. So that if I want to calculate that, I know direct cost. But what is the cost from V to Z? What is the cost from W to Z? What is the cost from X to Z? That is not known to you. So how you will get that? You will get that from the neighbors. They will calculate their own. They will calculate the shortest one. And then what they will do? See, each one will inform you that, see, from my point to Z, the minimum cost is 5. V says the minimum cost is 5. So you knows that cost from V. You will not calculate that cost from the graph. You got the point? Is it clear? Now how we will calculate that as 5, we'll see. But we will calculate its own and then send the update to you. Similarly, X will say, see, from my point, from X to Z, the minimum cost is 3, and W will say, from my point to Z, minimum cost is 3. So at a certain amount of time, you will get updates from these three neighboring nodes. Now, for example, if you need to calculate distance from U to Z through V, what will be the cost? Anyone? Did you get my question?
10 হবে।
How much? 10.
10
U to Z through V. U to Z through V. So how I can calculate that? U knows direct cost, right? U to V, that is 2, known. What is the cost from V to Z according to V? 5. Right? So 2 plus
Yes,
5,
sir.
it will be 7.
Sir.
Now see this. See this. Is this clear now? Go through this example. Where is the problem? So there are three neighbors. You can see one is V, one is X, and one is W, right? So if I want distance from source U to destination Z, just I have to calculate the value through each neighbor. So first V, then X, then W. There are three neighbors. For each neighbor, you will have two values. One is known directly, right? So what is the cost, direct cost from U to V? 2, right? Is it correct? Please participate.
Yes, sir.
Yes, sir.
What we said from definition, a node knows the direct cost. This is the partial information, but it will not know cost from neighbor to the destination, that it will be informed by the neighbor. How neighbor calculates, we'll see. But there are two parts. One is direct cost, that is 2. Another one is V will inform the cost from V to Z. What is that value? 5, right? See, that is informed by V to you. We already shown that V informed you that my point to Z cost is 5. Now, don't worry about how we calculated that 5. Don't worry about that. Just think about, okay, you knows the direct cost and you knows the cost from the neighbors. Now, what you will do? You will calculate these 3 values. And then you will find out who is the lowest. What is the lowest one? Through V or through X or through W?
Through it.
Right, through X. It's very simple. So if we calculate here 1 plus 3, that is 4, and the U to W cost is 5, plus W to Z, W says 3. So 8, 7, 4, 8. Definitely 4 is the lowest. So that is the idea. So what you will do? You will forward the packet to home if the destination is Z to X, right? That is routing, that is forwarding. We have already done many examples. Is it clear? Shomik? Anamol?
Yes, sir.
Is it clear? If not clear,
Yes, sir.
please ask. If it is clear, say at least yes. I want to hear more yes or more no. Just not 1 or 2. Okay, so this is the idea. Now, I mentioned one question, how neighbors calculate their lowest cost. That is the same procedure, we'll see later. But the main idea is every node will iteratively update its own forwarding table like this. Whenever it gets an update from neighbors, it will recalculate. Suppose a little bit later, V says, okay, my distance to Z is 1 for some reason. 1. Then it will again recalculate. 2 plus 1, 3. Then it will, okay, this is less than the previous one through X. So it will then update through V. Whenever there is an update, it will be calculated. Until there is a time where there is no more update. In that case, we call a converged state or consistent state. Okay? Any question? If no question, let us move. Okay. So what is the key idea? Again, I have already discussed, I have already mentioned, but again, let us review the key idea. From time to time, each node sends its own distance vector estimate to the neighbors. So whenever a node gets a response, gets an update from the neighbor, it will recalculate its own distance vector. What is the distance vector? Distance vector is distance to all possible nodes. This we call the distance vector. So every node continuously updates its distance vector. Okay? And then when X receives a new distance, that means any update from the neighbor, with those values, it updates its own distance vector using Bellman-Ford equation. We have already known the equation. And after the recalculation, recomputing, if any update is there, under minor natural conditions, the estimate dxy converts to the actual list cost dxy. Actually, you can ignore this right now because it says capital D means estimate, but definitely there is a list cost theoretically. So when we get that list cost, finally, we got that small d, actual list cost. And when we say capital D, that is actually in the process. The process is going on. So still it is capital D. That means so far estimated cost. So after a certain amount of iteration, certain amount of number of steps, we will get, finally we will get the actual list cost path. Okay. So that is the idea. and we don't know how many steps we need because it depends on the topology. It depends on how the nodes are interconnected, how many nodes are there, how they are interconnected. So it's not possible to say exactly 5 steps needed, exactly 10 steps needed. It doesn't matter. But when it will be finished, we can understand this by seeing this. Okay, if we just think about a state machine, each node is doing according to a states. The first state is every node will wait for change in local link cost or message from neighbor. What it says? Suppose there is a cost 5 between U to W, right? For some reason means if there is a more load, if there is more congestion, more delay, definitely cost will increase or decrease. If a link is down, what will be the cost? Any idea? Suppose suddenly optical fiber cut down, so a link is down, then what will be the cost used by the node? Infinite, right?
Infinity.
Infinite, because there is no connection, so infinite. Or a cost can be changed, capacity increase, load increase, load decrease. Anyway, so if there is a change in the local link cost, the node will recompute. Whenever there is a change, since data changes, so recompute. Or there is an update from neighbor. Other than that, a node will wait. Okay. Next, after recompute the distance vector estimates using the distance vector received from neighbor or the change link cost. Then it will see, is there any update? Is there any change? If no change, stop. If no change, you don't need to notify others. But if there is any change, then the node must notify the neighbors. And this procedure will continue, cyclic. So that's where distance vector algorithm works. Every node is in a cycle. Continuously it being changed, and it will end when there is no more update. Clear? When there is no more update. So it's iterative and asynchronous. We already said it's iterative because it will work with steps. Asynchronous means it is not like all the nodes will send updates at the same time. Whenever a node had update, it will send. So it's asynchronous, not synchronous. And then it is distributed because every node computes its own table. In link state, again, go back to link state, every node has complete topology. So when it starts the calculation, it has no dependency on neighbors, right? But in this case, every node will continuously calculate its own table, and it is self-stopping. Self-stopping means if there is no more update or there is no update received, then okay, I am in the converged consistent state. Now let us go through an example. Very good example. You can also use your paper and pencil so that whenever we need, I will show you how the calculation is done. Also, you should do it on your own using your paper and pencil. Then it will be easier. Okay, how many nodes in this graph? Please use your message box at least to participate so that it will be understandable. If you have any question, you can also ask your question here. How many nodes? Why we need so much time? How many nodes in the graph? 9. Simple. Count. You can count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 nodes. See, these are very simple concepts. If you understand the logic, I have mentioned many times, if you understand the logic, networking is simple. If you don't understand the logic, you try to memorize, you try to see it as only as a theory, you have to memorize, then it will not be easy. So 9 nodes, and you can see not all nodes are connected to each other. For example, C is only connected to B. So how many neighbors C has?
1, sir.
1. Simple. How many neighbors E has? E for elephant, E.
4, sir.
4. Just see how many connections it has. Simple. So when we say distance vector, we have to understand that the neighbors will participate. The neighbors will only participate in the process. Okay. Now, see, t equals to 0. T equals to 0, it means we can say initialization. Same like in the linked state, we said in the first step, there is no calculation because node source will know the possible destination that are reachable. Similarly here, every node will initialize its distance vector. Distance vector means what? Distance vector means from this node, distance to every other node. So you can see distance vector in A. So dA to A is 0, very trivial. A to A is definitely 0. But in other, all other possible distances, only A has 2 neighbors. So you can see 2 positive values. dA to B equals to 8. You can see this one, right? And dA to D is 1. So why this is 1? Because you can see 1 here, because you can see 8 here, right? So very simple. A initializes its distance vector. Just A to V is 8 and A to D is 1. All other nodes are infinite. Why? Because
No direct connection.
right, no direct connection. So initialization is very simple, and that's why you call it t equals to 0. All nodes have distance estimates to nearest neighbors only. Everybody clear? It's very trivial. First step. If you have any question, please free to ask. Okay. So as I said, there are not all are connected. Okay, now all nodes send their local distance. So after the t equals to 0, every node will send their local distance vector to neighbors. Because this is initialization, so some kind of update is there, so they will send to the neighbors. So if you can imagine, A will send to B and D, B will send to A, E, and C. So every node will send to its neighbors. Very simple, right? Okay. So t equals to 1. Okay, t equals to 1 means what? See, this is asynchronous. Asynchronous means the first initialization value will be done by everybody, and then every node will send the updates. And then in the second step, every node will recalculate, right? Now, let us see how a particular node actually recalculates. If we understand one node's calculation, we will understand every node's calculation, the same procedure. So that's why you are calling it t equals to 1. Okay. In t equals to 1, every node will receive update from neighbors. Show me. You have a question?
Yes, sir. No, sir.
Okay. So after getting update, in this case, okay, every node will compute. We know every node will compute its own. We can show every node's calculation, but this will take a long time. There is one difference between linked state and distance vector again in terms of showing the calculation. In linked state, we have to show the calculation for only the source node. But in distance vector, every node is doing asynchronously distributed. So it's not like you can show in a single table all the changes. No, you have to show changes in all the nodes tables. But that will take long time, that will take long space, a large space. So that's why we will show for one particular node. And also in the questions, I think I will ask you to show the calculation only for a single node up to the second step or up to the third step. Okay. So every node will compute. Then after computation, if there is an update, again every node will inform the neighbors, right? Okay. After neighbors get the update, t equals to 2, that's the next step. Again they will compute. Okay. If there is an update, They will send the update to others. It will continue. It will continue. As I said, we don't know how many steps we need. Okay, and so on. So it will continue. But there will be a time, as I said, when there are no more updates, right? For example, for node E, there is no more updates. So you will not send neighbors, right? There is no more update for C. It will not send updates. But there are updates for A, for example. In that case, A will send the updates. So it's a continuous process. I think in the lab, you have implemented RIP, right? So you have given router RIP, then network A, network B, right? In one router. Until you give the configurations to another router, it doesn't work, right? So after you configured both 2 routers, 3 routers, all the routers, then they exchange their information and then they give you the routing table. So in this case, what we are trying to do, we are trying to do two things. We are trying to see what is happening using a magnifying glass. Okay? In the lab, you have configured, after a fraction of seconds, routers updated, you give a show IP route, you saw the result, right? But you didn't see how this entire thing is being done. So here, we are using magnifying glass. Every step, we are seeing how that is done. And second thing, what we are doing the entire process in slow motion. Instead of fraction of seconds, every step we are going through in slow motion. So think about that. The configuration done in the lab, in the theory, we are seeing what actually happened. Then it will be easier for you to understand. Now let us take a look at the iterative computations at nodes. We will use one node as an example. And if we can understand that, we can understand the entire procedure. Okay? And for that, we want to use B as the example node, T equals to 1. Okay, now tell me, who sends update to B from T equals to 0? Which nodes send updates to B? You can use message box also. From the initialization T equals to 0, step 0, which nodes should send updates to node B? This one. This one, okay? Who will send updates to B? Which nodes? Can you tell me? No idea? Did you get my question?
Sir, confused, sir. T equal to 0 সময় নাকি T equal to 1 এর সময়?
T equals to 1 এর সময়. T equals to 0 is the initialization, and then T equals to 0, every node will calculate their initialized distance vector, right? Then every node will send updates that we call T equals to 1. So in T equals to 1, B will get updates from which nodes?
Sir, A, C আর E.
Very good, very simple. Sometimes you think very complex, but things are very simple. So A, C, and E, because they are neighbors of B. Simple. So from these 3 nodes, B will get update. Now, how we can think about this? Okay, B has its own distance vector, but this you can compare to T equals to 0. Okay, so this actually B's initial distance vector, and then B will get update from E. Okay, and then B will get update from C, and B will get update from E. So 3 nodes will send updates to B. Now what B will do? Now you can answer that question. Remember, in the equation, what we said, we used 2 values. One is C and one is capital D. Can you remember? C is the direct cost at each iteration of the formula. C is the direct cost and D is the estimated least cost path from neighbors, right? So this is estimated cost from neighbors. Okay, from neighbors. I am writing in shortcut because I have already mentioned this. So for every value, there is a C, direct cost, and there is a D value. C value is known to be. What are the C values? This is a C value. This is a C value. This is a C value, right? So this is C B to A, right? This is C B to C. This is C B to E. Do you agree?
Yes, sir.
Very simple. So this part is known to be, but the rest part, for example, what is the distance B to I? B to I, there is no connection. So what B will take, for example, if we say I is the destination, then A will send DA to I, right? C will send DC to I, to B, all to B. And E will send E to I to B, right? So if I want to recalculate this part, DB to I, this is for example, actually B has to calculate all entries, not only for I. It has to calculate for A, B, C, D, all. But for example, if B now wants to update DB to I, then how many options B has? How many values it will get? 3, right? 3 options because it has 3 neighbors. And for each option, it has a direct cost plus it has a D value, right? Is it correct? For each cost to calculate, it has C value already known plus D value from the neighbors update. Is it clear? So now where? What is the destination? Based on the destination, you will get one value. Based on the destination, you will get one value. So from this, you will get every time, for every entry here, you will get 3 possible values. Out of this value, if there is a lower value, then that will be updated in the distance vector of B. Okay, let us go forward. Information is updated, and then B will calculate, and then how B will calculate. See the first calculation. So B will use this update from A, C, and E, and then every time it will apply the Bellman-Ford equation. Suppose B is the source, A is the destination. Then how many ways B can move to A? Anyone? Can you tell me? From B, if B wants to go to A, what are the possible ways? How many? How many ways? We are at the same, I am asking you the same question again and again. How many ways? See, how many ways means how many neighbors. I have mentioned this many times. The number of
3,
ways
sir.
is equal to number of neighbors. No, 3. B has 3 numbers. You don't need to physically search for the options. Then you don't need the algorithm. You can do it in your own way. If you want to search the path yourself, we are using the algorithm. We have to understand how the algorithm behaves. So the number of ways is always the number of neighbors. Doesn't matter. See, B is A is directly connected. But there can be a better way to move to A. But there is no way B can forward other than A, E, and C, because these are the 3 neighbors. So every calculation, you have 3 options. As you can see, for every part of the calculation, the source and destination is fixed. The source and destination is fixed. The source and destination is fixed. So what is being changed? A, C, and another one, E, right? So A, C, and E. Did you get my point? Just look at the formula. Is it clear? That is what I have discussed before I started the example. So there are three neighbors. You will get three possible values. For each possible value, there are two parts. One is direct link cost. One is a capital D. The direct link cost is known, right? CB2A. It is known to be, what is the value? 8. And DA to A, it is by default 0. But this D value, it gets from the neighbors. So DA to A, it will get from here. Although this is by default 0. CB to C, what is the value? Directly known. Right? Can you follow me? Yes or no?
Yes, sir.
Okay. Then CB to C1. And what is the value of DC to A? Where you will get that DC to A? In which table?
Sir,
Tell
infinity.
me. Table of
DV in C.
DV in C, right? DV in C. So C, whenever from source is C, you have to go there. C is table. So what is the D C to A? C D C to A. This is infinite. Okay, so you just put infinite here. Similarly, CB to E, directly known, C to B to E, that is what? That is 1 plus DE to A. Where you will get that? Ashik.
The DV in E.
Yes, DV in E. So you will get here. So that's why I am saying neighbors send updates. So why neighbors send updates? Because capital D value is not known to the source. It must get that value from the neighbors. So from DVE, we have to search for DEA. That is again infinite. So you can see one is 8 plus 0, 8. One is 1 plus infinite, infinite. One is 1 plus infinite, infinite. So finally the value is 8. That means it is not changed. So this is not changed. Similarly, you have to do the calculation for all nodes. See the second one, DB to C. Again, you have to apply the equation where the same possible intermediate nodes A, C, and E, right? And for each value, you have the direct cost, you have the capital D. Again, CB to A, that is what? That is B to A is 8, and A to C. What is A to C? You have to come here. You have to come in DV in A. So this is infinite. CB to C 1 plus DC to C, right? So this is again direct cost, but you have to go here. That should be obviously 0. And CB to E, that is 1 plus DE to C. So again, you have to go to DV in E. See, all these values are from the neighbors. So B will never change any value in other table. B will only change its own distance vector. Okay, so what is the value of this E to C? That is again infinite. So it is infinite, 1 infinite, it will be 1. No change. So again, this is of no change. Now, D, B to D. If I calculate D, B to D, see, again A, C, and E. There are three neighbors. Apply the same equation. B to A, 8 plus what is D, A to D? So you have to go A's table. A to D is equals to 1, right? CB to C is 1 plus D, C to D. You have to go C's table. infinite. db to e1 plus de to d. E to d you have to go here, right? So this is 1. So now 9, actually this has a mismatch. This should be infinite and this should be 2. Anyway, so ultimately it is 2. Now this value has been changed. Okay, so it is now becoming 2. So previously it was not possible to go from B to D. Now our algorithm find out, okay, if I go through E, then the cost is 2. Same equation I am applying again and again. Is it clear to everybody now? Any question up to this point?
No, sir.
Okay. So similarly, okay, I give you one part to do. Please do this one. DBE is again 1, so this is already not changed. Do this. DBF. Do this yourself. Use the formula, put the values, and find the final value and put in the message box. Do it using your paper and pencil. D, B to F. So previously it is infinite. Let us see whether it will change, and if changes, what will be the new value. Calculate and put the answer in the message box. Please do it by hand.
স্যার কোশ্চেনটা আবার বলবেন?
Just find out the value of DBF from B to F using the formula. Just do it yourself and give me the answer in message box. That's the question. We have done for DBA, DBC, DBDE. Now do it for F. Write down the equation, just put down the values, you will get the final answer. In this example, we are doing the calculation for B. So always there are 3 possible neighbors. So we get 3 possible values in the equation. If there are 5 neighbors, we will get 5 possible values. Nuzhat, you said 1. Is there any other answer? For F, D, B, F. Okay, Nazmus Sakib. 2. Any other answer? Mahmoud Hassan. 2. Very good. Any other? Nuzhat, can you check your calculation again? Yes.
Yes, sir. Sir,
Yes.
1 plus 1 to আমি 1টা প্লাস করি না।
Okay, good, good. Okay, Azizur Rahman, Samiuজ্জামান, very good. See, if you participate, Anika, Enamul, if you participate in the class, it is very easy to understand. Yes, Sultan. So all of you got correct, but you have to show. Yes, Tawfiq, Ashik, very good. So all of you have to show the calculation in the equation. So just don't do it with your intuition. Sometimes we think that, okay, if we use the equation, it will take more time. So let us do it. It is very simple. I can do it. But in the long run, it will not be, it will not save your time. It will waste your time. How? Because if you put the formula and if you do it without any missing step, you are confirmed. Even if it will take some minimal time, but you are not confused, you are confirmed. But if you do it with your intention, sometimes you made mistakes and you have to go back and then you have to do it again. So in the long run, it will take less time effectively if you show all the calculations. So that's why in the exam, if you don't show the calculations, you will get maximum 20% of the mark. So 80% you will lose. So you have to show the calculation, because we want to understand how the machine works. So see, 2, the same thing, the same possible options, put the values, and then you will get to. So similarly, you will do all these things. So it will be updated to 2, and then dbg, it is same as the previous one, not updated. dvh, again it is updated to 2, and then finally dbi, it is same as the infinite. So what b will do now, it will replace, it will calculate the new values, and it will replace its table with the updated one. So we can say this is the updated distance vector of b in step 2 at t equals to 1. Now, is there any change happened? Yes or no? Definitely yes, right? There are lots of changes happened in distance vector of b. So what b will do now? Send updates to the neighbors. Okay? Send update to the neighbors. So that is what b will do. Now let us see another example. Just like b, in this case we will see the example of c. So c has how many neighbors?
1, sir.
One, only one. So c will only get update from b. Again, I am in t1. C, the update we did for b in t equals to 1 will be available in t equals to 2 to the neighbors. But for example of c, we are again thinking about the distance vector at time t0 coming to c only from b, because b is the only neighbor. So c will update its own table, that is in t equals to 1. Same thing, it will compute, and it will compute in this way. Okay, now this is a c, there is only one neighbor. So in every equation we got only one possible value. Possible next one is 1. Doesn't matter who is the destination, c must go through b, the only way. So that's why in the equation you get one application, one value. Okay, then after all these things done, then c will update its table. C will then send updates to, okay, like this, and then send updates to the neighbor. Now the only neighbor is b, so it will send update to b. Okay, so this is your homework. Homework means actually you have to practice. So practice similar like b and c. Now you should do the computation for e. Just practice it at home. You don't need to submit, just practice. And in case of e, how many updates it will get?
4.
4. Simple. E has 4 neighbors. So see, who are the neighbors? B, D, H, and F. So all these neighbors will send their own distance vector in step 0 to E, and then E will calculate. The same thing, E will calculate its own table. Okay, so please do it yourself. I think it will
হ্যাঁ,
be.
আমাদের কি
Yes.
এক্সামে এটা এরকম বলা থাকবে যে মানে এটাকে সোর্স ধরে করতে?
Actually, source is not important here. I will specify for which node you should show the calculation. Definitely like this. Like for example, okay, show the update of B's table in step 2. But you know, to update B's table in step 2, you need to know the tables of neighbors in step 1, right? So I might ask like this.
Yes, sir.
Is it clear? Just the way we have solved, the question will be also like this. Any question, anybody? Okay, so that's end of our, we have seen 2 routing algorithms hands-on. You can also relate to your network lab configuration that we have just given command, and the router inside does all the other things. actually all the things is programming, right, done inside the router. So you are a programmer, so you can do it now. You know how these all these things are happening in the machine, right? Okay, now let us find some comparison between linked state and distance vector. Already the theoretical approach, based on the basic approach, we have differentiated linked state and distance vector. For example, linked state, every router will have the complete topology. In distance vector, every router will have the partial topology. But in terms of some other points like message complexity, you know, they need to exchange messages. So in case of linked state, if there are n routers, since linked state advertisements must be exchanged between them, so there are order of n square messages changed, so a little bit more exponential data needed. In case of distance vector, the messages will be only exchanged between neighbors. So in terms of message complexity, distance vector is slightly better, but again, number of iterations we don't know. In linked state, convergence, once the entire database, entire topology is received by a node, it can run the algorithm its own. It don't need to do iterations with the other nodes. Okay, but in case of distance vector, convergence time varies because it depends on how many steps, how many iterations we need, so that all the nodes are in a convergent state. Also, there are some other problems like may have routing loops, and there is a count to infinity problem. But right now, just don't worry about this. We are not going to that theory. We just need to know the basic comparative differences between linked state and distance vector algorithm. So in case of linked state, there are order of n square messages, and it may have oscillations. Oscillations means if link cost changing continuously, right? That means every node will be receiving the advertisements, linked advertisements continuously. So it's continuously will have to be in calculation. And then robustness. Robustness means if a router is malfunction, if a router is not perfectly working, or if a router is compromised by the attacker, hacked, in that case, what will be the behavior of linked state and distance vector? Since in linked state, a node is dependent on update from neighbors, so if a particular router is hacked or compromised, then that router can advertise incorrect link cost, that D, capital D value. So this incorrect link cost, sorry, that is in distance vector. In linked state, the linked state advertisement, if a router is compromised, that will send the linked state advertisement. Linked state advertisement only contains the data about links, about the link cost. So that can be calculated and sent incorrectly. And since each router computes only its own table in linked state, it will not be propagated. Other way, in distance vector, a router, compromised router or malfunction router, can advertise incorrect path cost, that capital D value. Capital D value is from neighbors, right? And that is a path cost, that is not a link cost. So that can be incorrectly advertised, and in that case, that actually creates a big problem for distance vector. That is called black holing. And but in this case, each router's table used by others, we know that whenever there is an update, that is sent to all the neighbors. So these errors will actually propagate in case of distance vector. So these are some of the differences, but there is no better and best. Many routing algorithms of linked state is used in large networks. Many routing algorithms of distance vector is used in large networks. So they have, every algorithm, every routing protocol has its own merits and demerits. But in this slide, we have shown some of the basic comparative statements about linked state and distance vector. Okay, if you go through the textbook, I think you will get more explanation, and it will be more understandable. So that is the end of algorithms. Now the last section, of chapter 5. It says making routing scalable. Now, whatever we have learned so far, this actually works in within a particular network, within local area networks, right? Now you think about the internet. Huge number of routers are there. Can you tell, okay, all the organizations will use the same routing protocol? Is it feasible? No, right? For example, UIU probably using RIP, then UIU are connected with a ISP, right? Internet service provider. UIU cannot dictate them, or they cannot dictate UIU using the same routing protocol. Now there is a big question. It is not feasible to implement same routing protocol to all the routers. Then how we will communicate? All routers identical, not feasible. Making the network flat, that means in a single network, all the routers, not feasible, not true in practice. So the question is, how in internet then we will control, we will scale these billions of probable destinations? And it is also not possible for a single router to hold all possible destinations, right? In that case, routing table will be large. And not only that, we have seen in dynamic routing, routers will exchange information whenever there is an update. The more entries you put in a router, the more networks you put in a router, the more probability continuously change will be there, right? So that is one big question. How in internet routing can be more manageable? The solution is administrative autonomy. In the chapter 1, we have defined internet as a set of huge number of local area networks. So we can call internet a network of networks. And we have also done IP addressing and subnetting, right? So we have divided a large major network into a number of smaller networks. One of the reason of doing that subnetting, they have many advantages, but one possible advantage is what? More control, right? More control. I want to only deny internet browsing in the programming lab. The programming lab is in a different subnet. So that gives us more control, right? Similarly, in the internet, all the routers are not in a single network. They are under different organizations. So what we can define a term called autonomous system or domains, AS. The definition is aggregating all the routers in regions, and that particular region will be controlled by a single organization. So one single organization might have multiple autonomous systems, but one autonomous system cannot be controlled by more than one organization. One single organization can have multiple autonomous systems, like large ISPs, they can have many autonomous systems. All those they are controlling. But one single autonomous system must be controlled by a single organization. What is the logic behind that? Autonomous system will control the routers, and all the routers will use the same routing protocol. So that is manageable. Now we have another question. An autonomous system has all the routers implementing the same protocol, so it's fine, like RIP, like EIGRP. But then how we can communicate among the autonomous system, that is another question. When we browse from, for example, from Bangladesh to another country, to Yahoo, Google, Facebook, in a different country, maybe there are many ISPs in the middle, there are many autonomous systems in the middle. So from one autonomous system to the final destination, many autonomous system routers must forward that packet, right? So that is the next question, how routing can be done among different autonomous systems. So this is done by two types of routers. Already one type we have done, that is intra-autonomous system, intra-domain. That means these routers will work only within one autonomous system, right? And there are some routers, those we call gateway router, that is at the edge of the autonomous system, and they have links to routers in other autonomous system. So those type of routers are called gateway router. But the algorithms in intra-autonomous system cannot work in inter-autonomous system. So that's why we need second category of algorithm, that is inter-autonomous system or inter-domain, where routing can be done among a number of autonomous systems. How? Using those gateway routers. Let us show an example. Suppose there are three autonomous systems here: autonomous system 1, autonomous system 2, and autonomous system 3. You can see there are 4 routers in autonomous system 1, right? There are 3 routers in autonomous system 2, and there are 3 routers in autonomous system 3. So there are some routers like 3A, 1C, 1B, and 2A. They are actually connected to more than one autonomous system. So we call these routers what? Gateway routers. Okay. Simply, gateway routers are the routers, they communicate more than one autonomous system. And the other routers, like here, like this, they are called what? Internal routers. Okay. Internal routers. So internal routers only work within autonomous system, and gateway routers works between autonomous system. This is the idea. Now how it works? See, every autonomous system has some inter-autonomous system routing, and then there is inter-autonomous system routing between the autonomous systems. So inter-autonomous system is implemented by the gateway routers, and one example of inter-autonomous system is BGP, that is, sorry, border gateway protocol. Okay, border gateway protocol, but we will not study it in this course. Just we are trying to get an idea how internet controls the routing. Okay, so the idea is, now every router will have a forwarding table. That gateway routers will have a forwarding table that has both intra-autonomous system routing protocol and inter-autonomous system routing protocol. So what inter-autonomous system routing protocol will do, they will forward the packet to a different autonomous system. Now when a PC connected to this, right, it wants to forward a packet to a destination connected to, for example, autonomous system 3 or 2, then the routing table will be maintained in such a way so that they will be advertised to the internal routers also. So this 1D will know, okay, the destination is through autonomous system 2, so I have to forward the packet to here. This is, the concept is similar to default, not the default, but the similar to default. I think you have implemented in the lab, default routing. So the routing table will contain some entries that will help a router to forward to the correct gateway router so that it will finally reach to the correct autonomous system. So that is the idea. So in this case, suppose router autonomous system 1 receives a packet destined outside of autonomous system 1. We don't know it is autonomous system 2 or autonomous system 3. So what it will do, router should forward. So it is received by an internal router, even not by a gateway router. So router should forward the packet to gateway router of autonomous system 1, theoretically, right? But there are 2 routers, 2 gateway routers in autonomous system 1. Should it forward to 1C or 1B? That is the question. And the inter-autonomous system routing protocol actually take care of this. It will learn which destinations are reachable through autonomous system 2 and which destinations are reachable through autonomous system 3, and then propagate this routing information back to all routers in autonomous system 1, including the internal routers. So the first router receives, it actually knows it should forward the packet to the proper gateway router, either 1C or 1B, based on the destination autonomous system. Is it clear? So we are not going to any algorithm. but we are just trying to get the concept how in internet the packet is traveled between the ISPs, and ISPs contain autonomous systems, and routing table must take care of those. Okay, and there are some examples. I think I have already mentioned. RIP is a intra-autonomous system routing protocol. It is distance vector, no longer widely used. Why? I have mentioned some reasons. It has some limitations. And EIGRP, it was formerly Cisco proprietary, but now it is generally open to all. It is also a distance vector based protocol, in enhanced interior gateway routing protocol. And there is another one, that is OSPF, open shortest path first. This is a link state routing protocol. There is another one, IS protocol, ISO standard. So these are examples of intra-autonomous system routing protocol. And as I said, we are not working with inter-autonomous system routing protocol. I think there is an error here. It should be intra, not inter. It should be intra. Sorry for that. Inter-autonomous system routing protocol. And we are not dealing with inter-autonomous system routing protocol here, but I have given you one example, that is BGP. So inter-autonomous system, you can just BGP. There are some descriptions about BGP in the textbook, but we don't need that. Okay, so that is end of our chapter 5. Okay, any question, anybody? We have our next class test 5 on next Saturday, right? 25th.
Yes, sir.
And the syllabus will be 4.1, 4.3, and 5.2. So if you just complete your homework, okay, for homework, I think for many of you have requested to increase by 1 day. So I will increase the deadline from 24th to 25th. But my idea was you can, if you practice the homework, your class test preparation will be done. So it will, your homework will also cover your preparation for the class test on 25th. So anyway, I will increase 1 day. So it will be 25th midnight deadline. And as I said, all the examples you have done in the class. I will update the syllabus in ELMS. Okay. Any confusion, any discussion? Okay, if no more question, let us respond